All right.
All right. And Max, I'm going to introduce hi everyone. Welcome again to our weekly presentations. We had a good turnout last week. Right now we're up to 28 participants, and hopefully we'll get even more as we proceed tonight. Just want to remind everybody of the instructions, just in case it's your first time coming in. Everybody's going to be on silent mode, of course, except for the speaker. That's so there's no confusion and people won't be talking over one another. Max will give his presentation. You'll be able to see his PowerPoint. I think you can see it now. Once he's completed it, we can have time for questions. And if you remember, if you scroll down toward the bottom of your screen, you'll see a Q&A icon a little bit to the right. And you can type in your questions there. Max can read the questions out loud and answer them. All right. And maybe if there's time afterwards, we can open it up. If anybody wants to stay on after the question and answer period, we can open it up so everybody can see each other and we can talk. So, all right. So now I'd like to introduce to you Max Watzky. He is a member. He's a high school student. And I think, Max, correct me if I'm wrong. I think you're a freshman. Is that
That's
correct?
yeah.
Freshman. Okay. And Max had given a presentation before, I believe it was back in January, Max. I should have
That's right.
checked yeah. So I'm really glad that he has wanted to come back and do this, especially in this format. So Max, I'm going to let you take it away. So go ahead.
Great.
I
Thank you.
hopefully everybody can see his picture. Go ahead.
All right. I'm going to be presenting on living space junk. The name of the presentation, Living Space Junk, isn't a scientific one, and it's a little misleading and clickbaity. Actual space junk is made up of dead satellites and chunks of old spacecraft drifting around in Earth orbit. These stray pieces of hardware could set off a chain reaction of destruction if they collide with each other or active satellites, creating thousands of pieces of particulate, which could pose a serious threat to our network of technology in space. Living space junk is pretty different from actual space junk. The process of bringing living space junk to a celestial body is another way of saying that we contaminated that celestial body with our own Earthling life. The key similarity is that both living and regular space junk could pose a serious threat to human space exploration. I'll be talking a lot more about that soon, but in order to understand how we can contaminate other planets with our own life, we need to talk about the requirements for that kind of life to survive in the first place. Tell me if you can see the next slide. Okay,
Yes.
right.
Yes. Mhm.
The common denominator for all life that we know of are the requirements of water, which is used for digestion and regulating temperature in most organisms, among other uses, energy to power essential functions like movement and chemical reactions, and other nutrients like fats, proteins, vitamins, and minerals, which are necessary for all sorts of things. The wildcard requirement on top of these things is the right habitat. The right habitat means something different for every type of organism. Habitat might mean not living in a particularly hot or cold environment, or needing an environment with natural light, or an environment that doesn't have too much or too little air pressure. Because we found water, nutrients, and energy in the form of sunlight in other places in the solar system, difference in habitat is the biggest factor that could prevent our life from thriving outside of Earth. Um, the reason that I bring up habitat is that the conditions on other solar system bodies can be extremely different from Earth. To make my point, let's look at some of the places in the solar system that scientists believe harbor the best potential for life. Titan, one of the moons of Saturn, has water ice on its surface, a thick atmosphere, and soil that is rich in organic compounds and essential nutrients. However, its average temperature is a chilly negative 290 degrees Fahrenheit, which is cold enough that it has seas, lakes, and rivers made out of the greenhouse gas methane. For another example, Mars. Mars also has water ice and organic compounds, and its temperatures are a bit less extreme than Titan's. However, its thin atmosphere and lack of a magnetic field means that the surface is constantly being bombarded with UV rays and high energy particles that could pose serious harm to any life there. So, if conditions outside of Earth are so bad, why am I worried about interplanetary contamination? Well, it turns out that there is a class of organisms that could tolerate or even thrive in the kinds of conditions found on planets or moons like Mars or Titan. These hardy organisms are called extremophiles. Some are found in the intense cold of the Antarctic permafrost, and others are found withstanding huge amounts of pressure at the bottom of the ocean. Some, called polyextremophiles, can handle many different kinds of extreme conditions, like the bacteria Deinococcus radiodurans, which has been shown to survive extreme cold, dehydration, acid, and in a vacuum. These extremophiles could be pretty much the only kinds of organisms that would be able to survive the conditions on other solar system bodies that might be very different from Earth. However, even the toughest extremophiles have limits, which will be important when trying to figure out what we should do to prevent them from colonizing other planets. Uh, I have a short video here that goes a little bit more in depth on extremophiles and polyextremophiles. Oh, so let's see if I can get this to work. Okay.
Intense heat, freezing cold, high acidity, and radioactivity. These harsh environments don't seem hospitable for life, but some organisms not only survive, but thrive under such extreme conditions. The name extremophile means extreme lover. These organisms live in exceptionally harsh environments, such as hot hydrothermal vents or buried in rocks far beneath the Earth's surface. Extremophiles occur in all three domains of life: bacteria, archaea, and eukaryote. They range from the extreme heat-loving thermophiles, which feed off of inorganic chemicals and have special enzymes to survive high temperatures, to extreme cold-loving psychrophiles, which have evolved antifreeze proteins that help ensure their survival in some of the coldest waters on the planet. But the most extreme living things on Earth are tardigrades. Also known as water bears, these water-dwelling microanimals are polyextremophiles. This means they are capable of surviving multiple harsh conditions. They are nearly indestructible and have even survived the extreme conditions of outer space. Tardigrades have a unique adaptation that allows them to curl up into a dry, seemingly lifeless ball and slow down their metabolic rate. In this state, they can survive cold, dry environments like space for decades. Studying the adaptations of extremophiles may hold the key to solving many of Earth's problems. This includes the development of genetically based medications, producing new types of biofuels, and protecting people against radiation exposure. Extremophiles have opened our minds to the many possibilities of life and the environments that can support it. Understanding the limits of life in these extreme conditions on Earth may provide scientists with clues of how life could possibly exist elsewhere in the universe.
Okay. So now that we've moved past some of the fundamentals of interplanetary contamination, let's talk about the problems that arise when we bring our life outside Earth. One problem that could be relevant in the future is related to setting up colonies on other planets. When humans travel, we bring our microbes and viruses with us, which could cause all sorts of problems, like outbreaks of disease, as well as water or food contamination, which are problems that would not be good in an environment where interplanetary settlers would be packed into a confined space. A problem more relevant to modern space exploration with probes has more to do with the search for extraterrestrial life. Let's say that one of our polyextremophile friends hitches a ride on a space probe going to Titan, which has been tasked with looking for the signs of life. If the polyextremophile survives the trip and starts reproducing on Titan, it could pose some serious problems for that probe's search for life. It would be very hard to tell if any remnants of long gone microbes on Titan were actual aliens or just some polyextremophiles that we brought over. What would be even worse than this is if that polyextremophile colonized the entire planet with its offspring, which would render our search for life on the entire moon impossible. The prospect of something like this happening is very scary to astrobiologists, and as a result, regulations and guidelines have been put in place to make sure these polyextremophile invaders don't hitch a ride on our spacecraft. So what kinds of things are they doing? What should be done to prevent interplanetary contamination? COSPAR, which is the Committee on Space Research, a part of the International Council for Science, was tasked with this very problem in 1959 when they were put in charge of heading up the topic of planetary protection and interplanetary contamination. Every 2 years, when the 2000 or so Committee on Space Research scientists meet up, they are tasked with revising guidelines on interplanetary contamination. They divide up their recommendations on preventing contamination from unmanned spacecraft into 5 categories, depending on the kind of mission being carried out. Category 1 is for probes going to places that have no scientific value in regards to the origin of life in the solar system. An example of this is the sun. Not even extremophiles can survive conditions on the sun because its surface is almost 10,000 degrees Fahrenheit, which would instantly vaporize any organism. Its gravity is too great to withstand, and there is no solid ground. Because there's no possibility that life could survive there, there are no protections needed for the kinds of Category 1 spacecraft going to places like the sun. Category 2 is for celestial bodies that do have importance in the story of life in the solar system, but have a very remote chance of being contaminated because they are completely inhospitable to even extremophiles. One example of this is Venus. Even though Venus is interesting from a scientific perspective, but it all okay, Venus is interesting from a scientific perspective, but at almost 1,000 degrees Fahrenheit, Venus is also too hot for extremophiles, and its atmosphere is too dense. Poof. Category 2 also requires pretty minimal protections for spacecraft. Category 3 and 4 are for spacecraft that are supposed to orbit or land on planets with significant potential for present or past life. One example of this is Mars. Life could probably survive on Mars. Its conditions are within the bounds of certain public extremophiles, and contamination could severely disrupt our efforts to find life there. Even if a spacecraft is not meant to land on Mars, instead orbiting it, there is still potential that such a spacecraft could crash into the surface. So there are procedures that must be carried out to sterilize the craft regardless. Finally, Category 5 is for craft that are designed to bring samples of a celestial body back to Earth. These can have the very strictest requirements, but I'll be talking about that a little later on. First, let's talk about sterilization. Sterilizing equipment that's bound for space comes with its own unique challenges. We need to kill off anything that could cause contamination, like extremophiles and bacterial spores, which are notoriously hard to get rid of. But we also need to make sure we aren't damaging any sensitive equipment in the process. If you've ever seen pictures of NASA spacecraft being assembled, like in the image on your left, you've noticed some of the precautions being taken in order to avoid contamination. Spacecraft are assembled in clean rooms, which are routinely disinfected and specially built to greatly limit the amount of particles present there. In addition, engineers are required to wear special suits to avoid contaminating the spacecraft with any of the microbes that live in and on humans. Most spacecraft are sterilized with a method known as dry heat, where the spacecraft is exposed to hot air for an extended period of time, which gets rid of most microbes. Other methods, like exposing the spacecraft to hydrogen peroxide vapor, are sometimes used to disinfect spacecraft in order to protect heat-sensitive equipment. Uh, it's worth saying here that scientists are not all in agreement on the idea of sterilizing spacecraft. Some argue that the stress of space travel, like high amounts of UV radiation, extreme cold, and direct exposure to the vacuum of space, would kill any organism, even extremophiles. So there's no point in wasting tax money on trying to keep spacecraft sterile. However, others counter by referencing studies that have shown certain kinds of bacteria could survive space travel if they were in a nook or cranny of a spacecraft that was shielded from the coldest temperatures and the worst radiation, as well as our tardigrade friends. In fact, there is evidence that we might have already contaminated another planet with the Curiosity Mars rover. After the sterilization process on the rover was done, scientists took swabs of bacteria on it and found that over 10% of them were able to survive simulated space conditions. It's no stretch of the imagination to think that some of these kinds of bacteria could still be alive on Mars today, finally answering David Bowie's famous question, is there life on Mars? So everything I've said so far has been about the idea of forward interplanetary contamination, which is the idea that we can bring our microbes to other planets and moons. However, I have so far ignored the idea of backwards contamination, which is the idea that we could bring microbes from other planets back to Earth, which would most likely wreak havoc on the life already here. This is why Category 5 on the COSPAR scale has such strict requirements, like mandating that all return samples are quarantined or sterilized. The concern is that we might bring some sort of alien invader from Titan or Mars or a similar locale in such a soil sample. There isn't as much to talk about with backwards contamination because it's never happened before, and we've never found life outside of Earth. However, back in the days of the Apollo program, when finding life outside of Earth seemed much more possible and a lot bigger of a deal, backwards contamination was a lot bigger of a deal. Excuse me. It was such a big deal, in fact, that NASA kept the astronauts returning from the moon in the Apollo 11, 12, and 14 missions in quarantine for 3 weeks after they got back, out of the concern that they might bring some sort of moon microbe or moon plague home. The measures NASA took to keep these astronauts isolated were pretty strict. The astronauts were quarantined for 2 weeks, in addition, before launch, in order to make sure they wouldn't catch anything that could be later confused with a moon plague. In fact, President Nixon's request to have dinner with the Apollo 11 astronauts the night before launch was declined in order to keep the integrity of the quarantine. Then, returning from the moon, astronauts had to leave behind some of their equipment, which would limit the amount of moon dust and thus possible microbes they were bringing back. Once back on Earth, in their quarantine, they were kept in a special trailer. This trailer was sealed, you can see it in the first picture and in the second picture. This trailer was sealed off from the outside world and had lower air pressure than outside, so that if there was a leak, air would rush in instead of rushing out, carrying out a possible moon plague. The real kicker is that they did all of that without Zoom. Uh, According to Jonathan Eberhardt, writing for Science News in 1969, these astronauts weren't treated as heroes when they got back, but as bearers of the most virulent, devastating plague the world had ever known. These fears of a moon plague were not unfounded, though. If we brought back some kind of virus or microbe from the moon, we would have no immunity against it. Plus, it's really bad publicity for NASA. Um, with all of this doom and gloom, I'd like to start concluding this presentation on a lighter, more positive note. My final point is this: there could be a positive there could be a positive application for interplanetary contamination. You see, the idea of terraforming other planets to be more suitable to human life has been coming up more frequently in recent years. For example, Elon Musk, the CEO of SpaceX, wants to nuke Mars in order to heat up its ice caps, releasing water and carbon dioxide into the air. However, an easier and less crazy way of terraforming other worlds might lie in intentionally contaminating them with certain kinds of bacteria that could produce oxygen, making the atmosphere more suitable for human life. However, I wouldn't look into this too much. It's such a wacky science fiction-y idea that there's been barely any scientific research on the topic. Yet again, it's a pretty cool thought. With that, I'm just about done. I think it's time to open up the floor for questions, right?
Okay, Max, we have one question, but it's more like input. Isabel states that organisms could survive in the Venus clouds, but I would like to frame that as a question.
Okay.
Can organisms survive in the clouds of Venus?
Well, I'd imagine that any organism up in the clouds would probably fall back to the surface. I I haven't looked too much into the Venus clouds, but from what I know, it'd probably be possible if if they were living on some sort of orbiter. But if that orbiter was to crash into the surface, they would probably die.
That's a good point.
I do have a question personally. So I have this thought that what if the things that we imagine as aliens are really just things that we plant for the next civilization to rediscover as we travel through space? It's like a. But we do have we do have another question here from Frank. Have meteorites brought hitchhikers?
That's a really interesting question. There's actually this theory that the extremophiles and the polyextremophiles we have here are what's left of like a meteorite impact that was carrying one of them. Yeah, maybe.
It's an interesting point. Okay. Okay.
Oh,
Okay, one more question coming in here. How would monitoring of the procedures for sterilization be enforced?
So it's not really enforced. Uh, the Committee on Space Research doesn't really have any power, but their recommendations are followed by most world governments. Uh, but I think when I was doing the research for this presentation, I was reading about how a bunch of Russian spacecraft in the 1960s probably didn't follow the procedures, and we could have ended up with some interplanetary contamination from that. Um, Stephen's question. Considering the extremophiles' ability to survive in harsh conditions, is NASA studying their structure? I'm not sure. I haven't looked into that. But that's something interesting to research. Was this the reason the Cassini mission ended? Yeah, it was on track to crash into, I think it was Europa, and they didn't want to contaminate Europa because they had never done sterilization on it. So they flew it into Saturn. So do polyextremophiles have DNA, and if so, can't their DNA be used to distinguish between microorganisms that we may accidentally contaminate a celestial body with versus a microorganism that evolved organically on that celestial body? So it really depends on the kind of life we're talking about. We haven't sequenced the DNA of most extremophiles because I think some 90% of bacteria you can't culture in a lab. So it would sort of be hard if that extraterrestrial creature was DNA or RNA based to distinguish, especially if the remnants of that organism were really old and fragmented. So the answer is it depends.
Okay, looks like there are no more questions coming in.
Okay.
We'll give you another minute or two for any other lingering questions to submit. And Mary, I'll turn it over to you.
You've unmuted me. You unmuted me?
Yes.
Yes.
Okay. 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 Yes. Does anybody have any other questions? Because this is really good. I think there was no question. This is really good, Max. I really appreciate it. Very interesting. Especially, seeing the 5 different categories that they come up with to determine what is, let's say, safe, what they need to be careful about, etc. So I wanted to see if anybody had any other questions. Maybe at the last minute. We had up to 39 participants tonight. I really appreciate that. Okay, if that's the case, then George, why don't we, if anybody wants to stay on, and we can open up for people to talk with one another and to see each other.
Go ahead. You could pause the recording now, Mary.
Pause the recording. Okay.